Hey everyone, and welcome. Today, we're going to dig into something that's, well, at the absolute core of doing machine learning in science. How do we actually model our data? Because it turns out not all data is created equal. The story it tells depends entirely on how you decide to listen to it. So, let's jump right in. Okay, just think about this for a second. The recipe? It's just a list of instructions, right? Each one is its own thing. But that temperature log? That's a story. Every single minute is tied to the minute that came before it. This is the big difference we're going to unpack today, but through the lens of scientific data. So in the world of science, this usually breaks down into these two main flavors of structured data. Over on the left, you've got your classic tabular data. Think a big spreadsheet of material properties. Each row is basically a separate experiment, a little universe all on its own. You could shuffle those rows all day long, and it wouldn't change a thing. But then, on the right, you have sequential data, like a log from a sensor. And here, oh man, order is everything. Each row is just one moment in a long story. And if you shuffle them, you've just turned that story into complete gibberish. All right, so let's start with our first character in this story, tabular data. This is where every single data point is its own independent experiment. We're talking about a world of snapshots, right? A table of drug candidates and how well they worked, or a database of metal alloys and their strength. Each row is a self-contained, finished experiment. With this kind of data, our goal is to find these timeless patterns. We're asking questions like, what conditions consistently give us a better reaction yield? Or which genetic markers seem to be linked to drug resistance? We're trying to connect a set of conditions to a specific outcome. And it doesn't matter at all when or in what order those experiments were originally run. So the workflow for this is pretty robust, a great place to start. First, you've got to set up a simple baseline, something to beat, like just guessing the average every time. Then you bring out the standard workhorses, models like random forests or gradient boosting. But honestly, the most critical step, the one you can't skip, is the last one. After the model spits out what it thinks are important features, you, the scientist, have to step in and ask, does this actually make any sense based on the chemistry or physics I know? And that really gets at a unique challenge with scientific data. In fields like chemistry, experiments are expensive, they take time, so you often have just a handful of data points. But you can easily generate thousands of features or descriptors for each one. This short and fat data structure is the perfect recipe for overfitting, where your model isn't learning a real pattern, it's just memorizing the noise in your small dataset. And that's exactly why that final human scientific sanity check is completely non-negotiable. Okay, now for our second character, time series data. This is data that has a memory. Think about monitoring a chemical process in a factory, tracking reaction kinetics, or just reading data from an environmental sensor over time. In this world, the past isn't just a prologue. It's what actually predicts the future. Now, the key concept here, the thing that makes this data so different, is something called autocorrelation. It sounds fancy, but it's a really simple idea. Today's measurement isn't independent of yesterday's. They are linked, and ignoring that link is pretty much the fastest way to get your entire analysis completely wrong. This memory isn't just a statistical quirk. It's rooted in real-world physics. In hydrology, if it rained yesterday, the ground is still wet today, and that's going to affect the runoff. In water treatment, the chlorine you add doesn't just disappear, it decays over time, so today's level is a direct result of yesterday's dose. The actual physics of the system is what's encoded in that sequence. This brings us to the single biggest, most dangerous pitfall in time series modeling. It's a mistake that is so common and so sneaky that it can totally invalidate your results without you even realizing it. We are talking about the cardinal sin of data leakage. So what is data leakage? It's when your model accidentally gets to peek at the future. I love the analogy on the slide because it's perfect. It's like letting a student study for a final exam using the actual answer key. Of course they're going to ace the practice test, but have they learned anything? Nope. For a model, this means you'll see these amazing performance scores that just completely fall apart on brand new data. So this is the main point. And if you take one thing away, let it be this. It is the one rule you can never, ever break. Your test data must always come from a time after your training data. No exceptions. You're training your model to predict the future, so it can't be allowed to have already seen it. And here is what that mistake looks like. This is a standard random split where you just shuffle everything up. See the problem? Look at that test point on day 2. To predict what happened on day 2, our model has already seen data from day 3 and 4 during its training. It's predicting the past with knowledge of the future. That is data leakage, plain and simple, and it makes your performance metrics a total illusion. And this is how you do it right. You make one clean cut in time. We're going to train the model on absolutely everything that happened up to day 3. And then we're going to see how well it predicts day 4 and day 5. Now the model has zero information from the future. This is the only way to get a real, honest look at how well your model actually performs. So how do we actually do this? How do we teach a model about the past without accidentally showing it the future? Well, the answer usually isn't some fancier, more complicated algorithm. It's about being smarter with how we set up our data by creating features that explicitly give the model that memory. This is basically how we turn a time series problem into a regular supervised learning problem that we already know how to solve. For every point in time we want to predict, we just add new columns that describe the past. What was the sensor reading a day ago, a week ago? What was the average reading over the last 7 days? Now, a totally standard model, like a random forest, can use these new memory features to predict tomorrow using only information it's actually allowed to know. So we've looked at 2 very different kinds of data and 2 very different ways to approach them. But no matter which path you take, the process always ends in the exact same place, with a scientist looking at the result and asking, does this actually make any sense? So let's just recap the big takeaways here. First, don't overcomplicate things. Always start with a simple baseline. Second, especially with time series data, how you split your data is way more important than which fancy model you choose. Third, remember that when a model says a feature is important, that's a clue. It's not a scientific discovery. It's not proof of cause and effect. And finally, your most powerful tool is always your own domain expertise. Your scientific knowledge has to be the ultimate guide. At the end of the day, the best models are the ones that respect the physics of the system they're trying to describe. They have that reality baked right into their structure, either by respecting the arrow of time or by having their results validated against known science. So the next time you're looking at a data set, don't just ask yourself, what can I predict? Ask, what story is this data trying to tell me?